Afternoon, everybody, and you're very welcome to today's webinar hosted by the Energy, Environment and Climate Action Division. My name is Pat Kiernan. I'm Vice Chair of the division, and I'm ably assisted by Siobhan McHugh, who's our Chair at the moment. My day job is I am Director of Asset Management in Alternus Energy, and I look after solar parks. And I am particularly interested in today's webinar, end-of-life decisions making for wind farms, current status, challenges, and the future pathways for Ireland. My own background, I guess, is that we look at things from cradle to cradle, and repowering of any type of renewable energy asset is a complex thing. It takes a lot of thought and effort, but for the wind side, we are delighted to introduce our speaker, Abdollah. He is an associate professor from the School of Civil Engineering at UCD, and he leads the Structural Dynamics and Assessment Laboratory, and he's currently head of graduate studies in the school. His research expands structural dynamics, random vibrations, and data-driven modeling, with a strong focus on machine learning and statistical learning methods for monitoring, assessment, and decision support in complex engineering systems. Wow, that is quite a mouthful. So what I might do is hand over to Abdollah. He can give a friendly introduction and take it away.
Yeah, thanks very much, Pat. Thanks for the introduction. Very nice one. Hello, everyone. This is Abdollah Malekjafarian. As Pat mentioned, I'm an associate professor in UCD Civil Engineering, and today I'm delighted to be with you with this lunchtime webinar on end-of-life decision making for wind farms in in general, and in particular in Ireland. Before anything, I'd like to thank Pat, Siobhan, and Sinead for their kind invitation. So this is an honor to be here with Engineers Ireland on this topic. So let's get it started. I'll start from myself. As I said, I'm an associate professor here. So we've been doing a lot of research around renewable energy. So last year we made our own floating wind turbine, and we went to a competition in Belgium. So we didn't win anything, but it was a nice experience to see a real turbine working. So I've done a lot of teaching in Ireland, in our campus in China as well, and so I have a good research team around myself. I'm leading a structural dynamics and assessment laboratory in UCD Civil Engineering, and that includes about 9 to 10 PhD students and postdocs. And a lot of work I'm presenting today is basically their work, and I will refer to them at the appropriate time, but I really want to acknowledge their contribution to today's meeting. So let's get started with wind. So I'm just going to talk a little bit about wind and why is it important, and where we are in general in Europe, in the world, and in Ireland. And then we'll get to the topic of end-of-life decision and what we can do basically for this challenge. So as you can see, like a lot of countries are now pioneering in wind, and that includes both offshore and onshore. China now is a big player in the domain, but Europe always been a pioneer and doing really well in terms of amount of wind energy being produced. As long as we progress, you can see that in both offshore and onshore, the tendency is like towards larger turbines, larger capacity, and the technology is being advanced so fast. And so every year we're getting to better turbines, better capacity and efficiency. So, but at the same time, you can see that different countries in both sectors, offshore and onshore, across the EU, they're adding capacity, installed capacity. And this is basically a chart from Wind Europe, that shows that how much capacity with gigawatt is being installed every year up to 2024, and this is the projection towards 2030. That shows that more and more wind is being installed in Europe. And as a fact, again, according to Wind Europe, in 2024, 19% of the electricity demand in the EU was from wind energy. And quite interesting part, like if you look at the top countries in this chart, looking at Denmark, and right up there, we're talking about Ireland. And this chart is very interesting because it puts Ireland the ranked second in Europe in terms of wind generated electricity is like 33%. But at the same time, it has another interesting fact that we're talking about offshore and onshore, that almost all of that comes from onshore, and we're a little bit behind in terms of offshore wind turbines and offshore wind energy, which the government is trying to address that in the coming years. But what is the average lifetime of wind turbines? So wind turbines are interesting structures, and that unlike structures such as bridges, buildings that we designed them for a long time, 50, 100 years old, these structures are only designed for 20, 25 years. And when they get into the end of their life, then we need to discuss what is our decision, what we want to do with them. Before getting to what are the options, it's interesting to know out of those turbines being installed in the past years, what is the average age of onshore wind farms in Europe? So in this case, I'm just looking at the onshore because in Ireland, we're talking mostly about onshore. We only have one offshore wind farm, so we'll discuss that about that later on. But according to Wind Europe, again, so you can see the number of turbines with green that are 25 to 30 years, and also with orange 20 to 24 years. So that's a big number in, for example, Germany, Spain, which they started wind energy earlier on. And the dots here actually shows the average age of turbines in each of those countries. For example, in Germany, we're talking about 12 years. In Spain, which we have an older stock, we're talking about 14 years. Finland, 4 years, which shows that it's a newer stock or fleet of wind turbines. So that shows that some countries are going to face something serious soon, such as Spain. Germany already faced it, and they've been doing a lot of stuff there. So that shows that different countries, where are different countries in terms of the age of their stock, and then the need for end of life decision. Again, another interesting graph from Wind Europe is the commission and repowered capacity in Europe, different countries. And as you can see that as long as we're getting to the end of life of those wind farms installed back in 2000, those they need to either decommission, repowered, or we can talk about lifetime extension. So you can see that there is an increase there, which is directly linked to the increased number of capacity installed over those years. So this is also projected. The previous graph was up to 2024, and now we're talking about the projected to 2030. So it doesn't stop. So nobody's going to solve the problem. So the problem is going to get bigger and bigger. So we need to just come up with the right solution for those problems. So let's have a look at wind energy in Ireland. So we've talked a lot about Europe, the age of the stock, and where we are in general. When it comes to Ireland, the history of the wind, commercial wind, starts with Bellacork Wind Farm in Mayo, which was commissioned back in 90. And so it has 30 small turbines, each of them 225 kilowatt. And it was the first commercial wind farm and one of the earliest wind farms even in Europe. So that was the start of the story. But now we're talking about over 5 gigawatt of a milestone of installed onshore wind capacity, which that brought us Ireland as the second ranked wind player in the ranking that I showed you. And again, you can see that in 2025, one third of the energy demand in Ireland came from wind, which is pretty amazing for renewable. And if you look at the what is in the target, obviously the target for offshore is quite ambitious, but when it comes to onshore, we're talking about 9 gigawatt by 2030, which at the moment we're about five and a half. So we want to get into nine from five and five and a half. So that means that we need to install more capacity. But let's have a look at the number of wind farms in Ireland. So this is a study that we did as part of SAI granted a wind leader project. And so my colleagues, Afroz and Mohadisa, collected those data and Donaka. And we looked at all the turbines and wind farms in Ireland. We looked at 330 wind farms which collected from the SAI data sets. And this is basically the number of turbines and a cumulative maximum capacity of wind farms installed in the past few years. And it starts in 1992 and 2025. And you can see that if you're adding up to the stock. But this graph is interesting in terms of where we're getting the targets, but we should look at this part of the graph when it comes to end of life decision, because these are the turbines that installed back in 2000. And now we want to know, like, what is the age of those stock. So the number of turbines installed per year, onshore wind turbines in Ireland, and this is the age analysis of, again, a turbine installed in Ireland for the sake of end-of-life decision making. So you can see that when we're talking about 20, 25 years design life of wind turbines, a lot of wind farms now are exceeding those years. And that's not the only problem that we're going to face. We're going to have a lot of bigger numbers of turbines getting to the end of life. And now we need to see what is our strategy and how we want to make a decision for end of life for those turbines. So that's the landscape of the problem in Europe and in Ireland. And now let's talk a little bit about, what are the decisions and what are the options for wind farms. In general, this is a nice graphic I took from a US Ireland project, I think, so led by Paul Leahy and his colleagues in the States. That shows what are the options when it comes to a wind farm. So obviously we commission the wind farm, so we operate, and then it gets to the end of the life, and then we need to make a decision. And that decision could be lifetime extension, which basically means that let it to operate. Obviously, it's not as simple as that. Or just take it off, decommissioning, and that brings a lot of other challenges. Like, okay, so we want to take them off. What should we do with the material, with the composite plates, and the other stuff? And another type of decision could be repowering. And we'll discuss about these three options in detail in coming slides and see what are the options. So this is a little bit more comprehensive, basically version of the previous graph. Again, design, construction, operation, end-of-life decision, and that could be lifetime extension, repowering, and decommissioning. And repowering sometimes are partial repowering and full repowering, and decommissioning, it comes to a lot of other challenges, such as, decommissioning at sea for offshore, and how to transport the stuff, disassembly, recovery, landfill, which that was a big problem, and recycling. So the first option, lifetime extension. Lifetime extension means that we want to let the turbines work for more longer years, and this is like a continued operation of wind turbine beyond its design life. So it has a lot of advantages. First of all, that we can generate energy, and we can also avoid all of those hassles of decommissioning and recycling. At least we can postpone it for a couple of years, and these are the options that we have at the moment. There are basically two main standards available for how we can actually go ahead with end of life decision making in terms of lifetime extension. So one of them is IEC 6140028, and another one is DNV standard 0262, which talks about technical requirements for lifetime extension. And also we have another standard of DNV that talks about certification of lifetime extension. Basically, what those standards tell us is like how structured is these assessment and procedure of looking at the turbines and stock and collected data such as SCADA data, condition monitoring data, structural health monitoring data. And also look at the physical inspections, such as looking at the blades, hub, towers, foundation, things like that. And also using NDT approaches for crack detection and visual inspections to give us a little bit more information about like what is the status of the turbines, different at the structural levels and also the component levels. And they suggest three types of phases, like when it is in 15 to 25% of lifetime, which is a benchmarking approach, and 45 to 55% degradation, and when it is closer to the end of the life. That will help us to do pre-life extension technical basis. So IEC has also another important component, which is more about remaining useful life. And this is more about fatigue life of the main critical components of the turbine, such as the main shaft or so the tower, for example. So it comes at two different approaches for assessment: relative assessment and absolute assessment. And for the absolute assessment, we're talking about the deterministic assessment and also probabilistic assessment. So as I said, so the basis of this assessment is like we want to know what is the design fatigue life for the structure, and also what is the accumulated fatigue damage in the structure, and is there any useful life left in the structure or not. So this IEC basically talks about those. So relative assessment, it compares the design load parameters, which is used for certification, and also site-specific operational parameters. And then it applies to damage equivalent load, and it is suitable when models or parameters are not fully known, which is normally the case for all turbines, that we don't have a lot of information from the design from there. And the validation is very limited. And generally, it's less sensitive to modeling inaccuracy. But when it comes to deterministic and probabilistic approaches, so we can quantify the actual accumulated damage state, but that requires accurate definition of the machine characteristics. So, and also we need to well-define operational states and also reliable structural and load models. And then we use basic fixed input parameters. And in probabilistic approach, we incorporate measured loads, statistical variability, model and data uncertainty, and then we can have a probabilistic estimation of remaining lifetime. So that was IEC. So we have some sort of similar approach with DNV. So in DNV, we can talk about analytical assessment and practical assessment. And analytical assessment, we do calculate again remaining useful lifetime. And in practical assessment, we talk about inspection. So the main concept, again, is to compare original design condition versus actual site-specific environmental condition. And we can look at different components of the turbine. So in analytical assessment, we can look at the simplified approach and detailed approach and probabilistic approach again. And in practical assessment, again, we can look at the lifetime extension inspections and physical inspections, and then entire wind turbine for different components. So before getting to the certification, as I said, what we want to know exactly is if this is the machine and this is the condition that the machine is designed for, but that might not be the exact condition that the machine went through over the lifetime. So if we can get the data and information from lifetime and then apply to our assessment and calculation, then we can have a better vision what is going to be the remaining useful lifetime of the structure. And of course, certification is an important issue as well. So for lifetime extension, DNV suggests these parameters for basically a formal framework for certification of lifetime extension, which is important. Risk assessment is also important. The main concept in risk assessment is that whether continued operation is acceptable, and do we mitigate the do we mitigate the risks included in the concept of risk assessment. We don't want to go to the details of that. I just want to mention that that is an important parameter here as well. Operation, maintenance, and inspection requirements. So obviously, wind farm operators, they keep a record of the maintenance activities that they've been through. So those information also can come into the final conclusion in terms of end-of-life decision. And the maintenance normally are preventive and also corrective. So both of them can be an input to the end-of-life decision. Condition and structural health monitoring. So condition monitoring is basically we're looking at the condition of the structure. So we can collect and record the data, and that could be SCADA data and all the other information that you have. And at the same time, SHM is also an important and powerful tool, less implemented in real life, at least in onshore. So in offshore, I've seen a lot of cases that SHM is more implemented because those structures are more critical, and in terms of having access to repair of those structures as opposed to onshore wind farms. But basically, we install different types of sensors, like accelerometers, strain gauges, to have a better idea of stress distribution and fatigue life accumulation in the structure, for example, in the tower of the wind turbine. And when it comes to those approaches, so it helps us to detect degradation, and it supports RUL, remaining useful lifetime, and also reduce the uncertainty. That's important when it comes to, because all of these approaches that we're using standards, that includes huge uncertainty. So SHM help us to reduce that, and also that helps us to do predictive maintenance. Basically, if we detect anything in the structure, we can basically detect it at the right time before it's getting a big problem. So I'm going to just show a couple of slides about a recent inspection and monitoring that we did on a turbine in Balakirk before it gets decommissioned. And I know everyone knows that this wind farm is now decommissioned officially. So as part of, again, the SEI funded project, in collaboration with my colleagues, Vikram Pakrashi and Tom Kalan, and it's a big group, Shane Holden. So we did investigate foundation, and we did drone-based inspection, and also strain gauges, laser barometers, and also accelerometer-based monitoring. So these are a few examples. So in terms of foundation inspection that we did, so we looked at the quality of concrete and rebars in the concrete, and we also use drone measurements, so to see if we can detect any defects and damages at the surface of the turbine, including tower and blades. And also use laser vibrometers to measure vibration, and that helps us to create a model from the structure if you have the model parameters of the structure. And also we looked at installing accelerometers, wireless accelerometers, and we detect some vibration to find out the structural components of the structures. And that again helps to build up the model and reduce the uncertainty. So that was an example, and so the conclusion was that the foundation of the structure was in really good state for that type of turbine, and even the tower and the blades were in a good condition. So the second option after life extension is repowering, and repowering again. Uh, so that could be a decision that can be made at the end of the life. It has a lot of benefits. It can help us to continue the operation, and potentially it could be in some cases cheaper than building new turbines and wind farms. And so we can potentially use fewer turbines, because when you're looking at repowering, you can basically replace turbines that are 20 years newer in terms of technology compared to what installed 20 years ago. And that will help us to have better energy cost. So a lot of time, so planning permission and stuff could be useful. Could be we can save time on planning permission, or sometimes we can waste time on planning permission when it comes to repowering. One of the main challenges in repowering is actually planning permission, because everything was issued based on the original wind farm, and now we're talking about a new wind farm. So another option is partial repowering versus full repowering. For example, in some countries, when they started the journey of wind, after a few years, they figured out like they can have better blades. Then basically they did partial repowering to a lot of wind farms there, and they just replaced the blades, they increased the capacity of energy and output electricity. And then that it was repeated a couple of years later with a new gearbox. So that could happen as well as an option. So basically, you keep the turbines, the same number of turbines, and you replace the components with newer components that could give you better energy production. Or full repowering is normally like, you remove smaller and less efficient turbines, and you install larger turbines with more capacity. And that means that you can replace, for example, a wind farm with 30 turbines with a few, 7 or 8 larger or more modern wind turbines that will give you the same amount of energy. So as I said, like the partial one could happen in any part of the structure. But when it comes to full repowering, which means that removal of the existing turbines and installation of new turbines with larger hub height and rotor diameter, it will come to a lot of different challenges. As I said, the first challenge is planning permission restrictions, and a lot of cases for the original certification. So you have height limits and you have noise and visual impact. So you're looking normally at larger turbines, which larger with taller turbines, and that is actually a problem with those stuff. And land use conflict and transfer logistics for large components and grid connection sometimes, and local community acceptance, and these kind of stuff normally lead to, again, delays in permission. And finally, this should be number 3, so not number 2, but the third option is decommissioning. And decommissioning is clear. So we're talking about removing turbines, and that's the end of the life of the wind farm. And then you're not going to put any new turbine in the location. As I said, lifetime extension and repowering are possible option, and basically favorable option for us. We want to have energy production within the wind farm, but it's not always the case. And sometimes we need to go towards decommissioning as well. And so again, decommissioning is not as simple as what we're saying, like you just remove them. No, we have to go through planning. We have to go through dismantling and transport logistic, and most importantly, so waste management and monitoring and site recovery. So landfill used to be a big problem in the past, and now most of the countries in Europe, it is forbidden. So that means that the blades need to be either repurposed or recycled at the point of decommissioning. So the problem with the old composite blades always used to be like that. These are not easily recyclable, and you need to find a way basically to use it in some other places. So technology has improved a lot. So the newer turbines are recyclable. But at the moment, we're talking about those wind farms that are installed 20, 25 years ago. So that still is a problem for us in terms of decommissioning and end of life decision making. So when it comes to decommissioning, so we have the planning step, and that includes economic assessment and regulatory approval, and operational planning and environmental impact assessment. And the second step is dismantling and all of those stuff, and how we can actually plan the logistics of that. And as I said, more challenging part of that is basically waste management and site recovery. So you can see like a really nice graph. Again, I think I forgot to put the reference here. I think that comes again from, if I'm not mistaken, from WinEurope. And that shows material flow in a Vestas 390 wind turbine. And you can see that the type of material, which could be copper, steel, concrete, aluminum, but and polymers materials. So those are basically what is in the blade, and concrete stuff is something in the foundation, and steel all over the place. So you can talk the object in the turbine. So it's basically the turbine itself, and the material is mapped to that part of the turbine, and foundation and the other stuff. And when it comes to end of life option at the moment, and what would be the end of life option, which is the best option, you can see that a lot of that comes to landfill or what is basically in terms of concrete. But for the steel components, so we can have a lot of recycling in steel component. And so what ideally we want to have is as much as possible in terms of recycling for all types of materials, and also reuse of those materials with all different techniques or approaches that we can have, and as minimum as possible in terms of landfill if it's possible. But how big is the problem? The problem is pretty big. If you compare the tons of materials, basically wind turbine blades, for example, from 2018 and projection towards 2050 versus different countries, that's going to be a really big problem for countries like China, that they started a bit later, but now they're speeding up the wind generation. So in Europe, it's pretty straight. So, but as you can see that, so the blue bars are for China, that they will face a big amount of wind turbine blade waste towards 2050. Another option could be repurposing, and this is a really nice study based in DTU in MTU in Cork. So my colleagues Wesna, Yartsik, and Kieran and Paul Leahy, as part of Airblade project, they looked at how they can use wind turbine blades for a bridge, and so obviously. Those blades are not designed for this purpose, but when it comes to bringing them for different applications, so a lot of assessment needs to be done. So they've done a lot of testing, load testing on those blades, and that is now in operation as a real bridge in Cork. Other options could be using the turbines blades for so playgrounds, and another example, a nice example here for signs in motorways, and other options, for example, bike shed, and a lot of different applications at the moment in Europe. They're trying to look at how they can minimize the process of recycling. So they want to use this blades repurpose as much as possible. Another interesting example I saw in Ven Europe, the latest Ven Europe conference, was like to use the composite material as aggregate in concrete, and there was a Spanish company, so they're using it at the moment. So it's a very successful application of repurposing and reusing of the blade composite waste. Now, so these options were like the options that we have and the standards that we have. But what we wanted to do in this project was that, okay, so let's make it a little bit more structured and see what are the options at the end of the life. And we came into this idea of creating a decision-making framework. And so this is, again, a framework that we developed. It's led by a master's student at the moment at the UCD, Danaka Murphy, sorry, and my other colleagues, Afroz and Muadza. So we came to this end-of-life decision-making framework, and so that means that we're suggesting how we can choose the preferred pathway. So we'll start with wind farm reaching end of life, obviously, and data collection. And then we're talking about the criteria. So for the evaluation. So we concluded that we have four main items or criteria to make a decision. So the first one is obviously technical, but that's not everything. So you might have technically approved or proved that, a turbine can be extended, the life of a turbine extended, but we need to look at the other parameters as well. So the second one would be economic criteria, regulatory criteria, environmental, and waste management. And at the moment, we're trying to create a multi-criteria decision assessment and analysis, and then which will lead to preferred pathway. And that pathway could be decommissioning, lifetime extension, partial repowering, or full repowering. So for all of those criteria, we look at the details of those criteria, and we're trying to give basically weight to those criteria and how we can actually rank those criteria. So if we go to each of those, for example, in terms of technical criteria, so the main purpose is to determine the remaining useful life of wind turbine or major components or the whole turbines, and if that is enough for lifetime extension or not. And that is basically based on model-based assessment or inspection assessment and operational maintenance history, and the output of that will be to define or determine if RUL is enough or not. The second part is economic criteria, and so we want to assess final financial performance and risk of each of pathways. So that will include the revenue potential. Obviously, I mean, that's not my direct expertise, but that's something we need to consider into it. And CapEx and also operational maintenance cost. And then we looked at the economic feasibility score for each of those options. So in terms of regulatory criteria, we're looking at these few items: regulatory permissibility and burden and decommissioning obligations. And at the end, we'll have a score for regulatory constraint. And finally, we will talk about environmental and waste disposal criteria. And for each wind farm, we can give a score in terms of each of those pathways. And that comes from waste recovery potential based on circularity, performance, and also feasibility of composite blade management. And so what we're doing at the moment, obviously it's not completed, is to try to put everything into a framework, and we want to test it on a few wind farms approaching end of life. We have data information from a wind farm in Portugal, so we're working on getting data from Ireland as well, from a few operators. I mean, if there are people from audience that are interested, so we would love to hear from them. Basically, you can see like what is the framework, what was the input, and what are the output, and we want to test that if that framework gives the right answer or not, or is that something reasonable or evidence-based for end-of-life decision making in Ireland. Okay, so now I'm getting almost to the end of my presentation, and for the concluding remarks, I have a few items to conclude. So as we saw from the graphs or age analysis in Ireland, we're looking now the time that we have a lot of turbines and wind farms getting to the end of the life, and I think now is the time to make sure that we have a good framework and a strategy for end of life decision making, and that is not just technical, and that includes all the criteria that we need to bring into account. So as I said, lifetime extension is no longer a theoretical option, so it requires a structured, standard-based assessment, and it needs to be supported by high-quality monitoring and inspection data. That's the problem in a lot of cases, that inspection data is not always available, especially towards the end of the life. And we always think that, so last year we can install a couple of sensors and get some data, but that's not enough. So we want to get early enough before the end of life to get more information about the structural component of the turbine to have a better lifetime extension estimates, basically, and that basically moves to calculating or estimation of remaining useful life, and that needs to be moved from deterministic assumptions towards uncertainty aware and probabilistic approach and risk informed approach that can help us in terms of decision making. SHM techniques. Well, I mean, I'm coming from SHM background, and that always is something interesting for me. Of course, in wind energy, that's really helpful. That helps us to get a better idea about the dynamics of the turbines and the structural performance of turbine, and even making a model from a turbine that needs SHM basically techniques, and that could be a strategic tools for us. Repowering is a good option, but again, planning constraints and other constraints such as grid limitations and community acceptance are the bottlenecks for us. And decommissioning is inevitable for turbines at the end. It doesn't matter if you extend the life or repower the turbines. At the end, you need to do recommissioning. So circular economy strategies, especially blade repurposing, those can help us to avoid future waste challenges as much as possible. And my final conclusions are we need to have a framework which is supported by data for end-of-life decision-making. And that's not an easy job, of course, and we can talk about that for a long time, but it's better to define those criteria and create the framework and then work on it. So the key question is no longer can we extend life, but what is the optimal pathway for each of those assets? So a lot of things that I presented here are coming from our recent projects. So Wind Leader and also Remote Wind and also Nexus project. Thanks very much.